An attestation from instructor Carlos focused on Durham School shows that I've committed my entire calling to cultivating a specific theory about the universe. Then, this happens, the theory is being tended to. I embrace this test, since it is through such investigating that we advance and gain ground in science. The James Webb Space Telescope is challenging some extensively held convictions in cosmology that have been accepted as truth for a century. A newly obtained image reveals that we may have made mistakes in space science. This telescope, initially intended to uncover the first stars of the universe, has revealed findings that might completely alter our current perspective. While some experts find these revelations unsettling, many scientists welcome the changes, as there have long been issues with past speculations. The anomalies in assessing the universe's development rate alone should have alerted researchers years ago, rather than clinging to outdated theories. The cosmic microwave background radiation, CMB, which represents the oldest light in the universe, emerged around 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to form stable hydrogen atoms. This phase, known as reionization, made the universe transparent to light. The CMB was first detected in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on new antenna technologies and encountered a pervasive signal coming from every direction in the sky. This discovery, initially thought to be noise, ultimately bolstered the Big Bang theory. Penzias and Wilson received the Nobel Prize, and their finding became foundational in the history of astronomy. The CMB offers insights into the early universe, with subtle temperature variations revealing critical information about the universe's conditions shortly after the Big Bang. Scientists have used the CMB as a reliable benchmark to estimate key aspects of the material universe, including the universe's expansion rate. Edwin Hubble had already begun making such assessments in the late 1920s, observing that distant galaxies are receding from us and that their speed correlates with their distance, now known as the Hubble law or Hubble constant. Although Hubble's initial estimates were not entirely accurate, they were groundbreaking. When the CMB was discovered, researchers recalculated the expansion rate, finding it significantly lower than Hubble's initial estimation. Later recalculations using Type Ia supernovae as standard candles provided a more accurate assessment, but discrepancies persisted. The difference in expansion rate assessments has been known since the 1990s, leading researchers to suspect issues with CMB data analysis or universal expansion models. This inconsistency, called the S8 tension or Hubble tension, suggests that our understanding of the universe may be fundamentally flawed. Since the James Webb Space Telescope began its operations, it has provided astounding data that could help address these issues. Observations of extremely old and mature galaxies indicate that their formation may have theoretically begun even before the Big Bang, challenging old scientific theories. Cosmology now faces what many consider the greatest crisis in modern astronomy. The expansion speed of the universe and our theories about the origins of everything are under scrutiny. New images reveal a universe that diverges significantly from previous models. The S8 tension served as an initial warning, and researchers who held on to outdated theories now face a situation where numerous experts are grappling with the possibility that our understanding of the universe may be inadequate. This uncertainty has left many researchers troubled and bewildered. To tackle this crisis, it's essential to understand how science works. Theoretical scientists use a blend of mathematical models, observational data, and logical reasoning to reach conclusions. Their knowledge stems from observing patterns, experimental results, and hypothetical analysis. The term theory itself implies assemblies and reflections rather than absolute truths. Our scientific knowledge comes from images provided by telescopes, sound waves, and radiation captured by radio telescopes, as well as data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to break down the oldest light into individual frequencies, examining it in unprecedented detail. It reveals which elements existed in galaxies billions of years ago, the mass within them, and the number of stars present. However, Webb's images present challenges. For example, it cannot easily distinguish between galaxies and black holes that emit the same brightness due to massive accumulations of matter. Our scientific observation has evolved to recognize multiple possibilities as insights, often disregarding other explanations. New revelations from the James Webb Telescope provide invaluable clues that might replace outdated theories with new understandings. Researchers now face revelations so distinct that developing new explanations is challenging, and recent discoveries are shaking the foundations of physics, sparking concern among many experts. Physics education today remains strongly influenced by Isaac Newton's 17th-century work. For centuries, his laws of motion and gravity laid the foundation for understanding the physical world and the universe. Newton's laws explain the movements of objects under standard Earth conditions. However, in space, his ideas needed expansion, a feat largely achieved by Albert Einstein in the 20th century. Einstein's special theory of relativity, published in 1905, transformed our understanding of time and space as relative to the observer's movement. His general theory of relativity in 1915 furthered these ideas, using mathematical proofs of gravitational phenomena based on the curvature of spacetime caused by massive objects. While Einstein's theories clarified many areas, he acknowledged their limitations and sought a unifying theory, an endeavor that remains unfinished. It is fascinating to consider where potential errors might lie. Michio Kaku, a prominent American astrophysicist, proposed that solving this issue could lead to a Nobel Prize. We need to examine what researchers might have overlooked, whether there have been misunderstandings of quirks, or if there are flaws in our telescopes. Dark matter and dark energy are prime suspects in the cosmological dilemma. Current models estimate that dark matter and dark energy together make up about 95% of the universe, yet neither has been observed or proven definitively to exist. They may not exist at all, or they may possess properties that we do not yet understand. This uncertainty has driven researchers to consider a range of theories, from adjustments to current models to entirely new paradigms. For example, some propose that dark matter could consist of more exotic particles than previously theorized, or that dark energy might represent a new fundamental force. Similarly, cosmological studies investigate cosmic inflation, the theory that the universe experienced rapid expansion in its earliest moments. While inflation theory has explained many aspects of the universe, such as its homogeneity and isotropy, it also raises questions about the nature of the inflationary period itself. The search for extraterrestrial life remains a major motivation for cosmic exploration. Discoveries of exoplanets, or planets orbiting stars outside our solar system, have opened new possibilities for studying life-supporting conditions. Advances in telescope technology, like the James Webb Space Telescope, allow researchers to analyze the atmospheres of these exoplanets for potential biomarkers. The discovery of life beyond Earth would have profound implications for our understanding of the universe and our place within it. In theoretical physics, string theory and quantum gravity represent two different approaches to unifying our understanding of fundamental forces. String theory suggests that the fundamental components of the universe are not particles but one-dimensional strings vibrating at different frequencies. This theory aims to reconcile general relativity, which explains gravity, with quantum mechanics, which governs particle behavior on the smallest scales. Although string theory is highly theoretical and mathematically complex, it has inspired new methods for exploring the nature of spacetime and matter. Quantum gravity, on the other hand, attempts to create a framework that combines quantum mechanics and general relativity. One primary approach is loop quantum gravity, which proposes that spacetime itself has a discrete, granular structure at the smallest scales. This approach seeks to bridge the inconsistencies between general relativity's smooth spacetime and quantum mechanics' probabilistic nature. The interaction between theory and observation in modern cosmology highlights the dynamic nature of scientific inquiry. As observational tools improve, our ability to test and refine theoretical models becomes more precise. For instance, gravitational wave cosmology has provided a new way of examining phenomena like black hole mergers and neutron star collisions, offering insights into fundamental gravity and matter under extreme conditions. These discoveries not only confirm assumptions about general relativity but also open new questions about spacetime. In summary, the reassessment of cosmological theories in light of new insights reflects the resilience of the scientific method. The James Webb Space Telescope and other advanced observational tools have provided extraordinary insights into the universe, prompting researchers to revisit and refine long-standing theories. This cycle of continual questioning and revision is essential for advancing our understanding of the universe and addressing the vital questions at the heart of cosmology and astrophysics. As we explore the universe, we remain engaged in a quest for knowledge that seeks to answer fundamental questions and inspires future generations to push the boundaries of human understanding.